Somewhere right now, in a quiet laboratory, there is a ring of metal so cold that the air around it would freeze in an instant. And inside that ring, a current is flowing. Not the kind of current that runs through the lamp you might still have on, the kind that needs a wall socket and a steady push to keep it alive. This current has no push behind it at all, no battery, no wire leading in from somewhere, nothing feeding it, nothing paying for it. It was set spinning once, a long while ago, and it simply kept going. It is going still. And as far as anyone has ever been able to measure, it always will. Welcome to the Curious Voyager. It's lovely to have you here tonight. Wherever you are, curled under a blanket, lying flat with your eyes already half closed, sitting up somewhere with a lamp glowing soft and gold in the corner, I'm glad you came. Settle in. There's no hurry in anything we're about to do. We are going to move slowly tonight, very slowly, the way you'd wade into still water, one careful step at a time, letting each idea settle before we reach for the next. You don't need to hold on to all of it. You don't need to hold on to any of it, honestly. If you drift off somewhere in the middle, that's perfectly fine. The ideas will still be here when you wake, and so will I. And before we go further, if you enjoy these slow journeys, a gentle like and a subscribe really do help this sleepy little channel keep going. Small creators like me rely on it more than you'd think. And to those of you already here, already part of this, who come back night after night, thank you truly. It means a great deal. I'd love to know too where in the world you're listening from tonight. What time is it in your corner of the dark? Leave it down below if you feel like it, before your eyes get too heavy. It's a small thing, but I always like to picture all of us scattered across the globe, lying still in the quiet at the very same moment. Now, let me try, gently, not to make this so interesting that it keeps you awake. Though I'll admit, what we're about to talk about is a little strange, in the loveliest way. So if it does keep you up a few minutes longer than you planned, well, at least you'll have learned something. A fair trade, I think. Let me come back to that ring of cold metal because I want you to really see it before we go anywhere near explaining it. Picture a loop, a simple closed loop of metal like a thin bracelet or the rim of a small cup. Nothing special to look at, but this loop is sitting inside a chamber that has been chilled to a temperature you and I will never feel in any ordinary life. Colder than the deepest Antarctic winter, colder than the dark side of the moon, colder than almost anywhere in the entire universe except the few quiet corners physicists have made colder still by hand. And in that profound, motionless cold, something has happened to the metal. It has become what we call a superconductor. We'll unfold exactly what that means together, slowly, over the course of tonight. For now, just hold the picture. A current was started in that loop, electrons set moving in a circle around and around the ring. In any normal piece of metal, the copper wiring inside your walls, say, a current like that would die almost the instant you stopped pushing it. It would fade out in a fraction of a single second, its energy bleeding away into heat, the way a spinning coin wobbles and falls, the way a pushed swing slows and, finally, hangs still. That's the ordinary fate of motion in our world. Everything that moves slows. Everything that flows eventually stops. We learn that so young we forget we ever learned it. It feels less like a fact and more like a law written into the bones of reality. But not here. Not in this ring. Here, the current went around once, and then again, and it did not slow. It did not fade. The electrons just kept circling, with nothing pushing them and nothing draining them, like a planet that has fallen into an orbit it will never fall out of. Scientists have watched these currents. They have kept them under careful observation, measuring with extraordinary precision, looking for the smallest sign of decay, the slightest weakening, the faintest hint that the current is, ever so gradually, winding down. And they have found nothing, no decay, none at all within everything their instruments can detect. And so they began to ask a different question, not how fast is it slowing, but if it is slowing at all, slower than we can possibly see, how long would it take to stop? They worked out the lower limits, the bounds that the experiments allow. And the number they arrived at is one of those numbers that when you first hear it, your mind slides off of, the way a hand slides off wet glass. The lifetime of such a current, the time it would take at the very most generous estimate the measurements permit before it noticeably weakened, is longer than 100,000 years. And when physicists sit down with the theory and try to calculate how long it would take for the current to simply, spontaneously, give up on its own, with nothing disturbing it, the number they reach is longer than the present age of the universe, longer than the 14 billion years or so that have passed since the very beginning of everything we know. Let that settle for a moment. A current set, spinning in a small ring of metal that would outlast the universe that contains it. Not almost forever, not very nearly perpetual. As close to literally forever as any human measurement has ever been able to reach. And here is where I have to be honest with you, the way I always want to be, because the honesty is part of the wonder. No one has actually sat and watched one of these currents for 100,000 years. We haven't been around that long, and neither has the science. That enormous number is not a thing someone clocked with a stopwatch. It's an extrapolation, a careful, well-founded reaching outward from what the measurements do show, which is no detectable decay over the years and decades we have been able to watch. From we cannot see it slowing at all, the physicists reason, with good mathematics behind them, to it would take longer than the universe has existed for it to stop. It's a reasonable, grounded estimate, but I'd rather you hold it as the beautiful, well-supported guess it is than as something anyone literally measured to the last digit. The truth is striking enough on its own. The current does not stop. Nobody has ever seen it stop. And everything we understand says it never will. Now, if you're anything like me, lying there in the dark, something in the back of your mind has already raised a quiet objection. Maybe it's half-formed. Maybe it's just a faint sense of something being not quite right. Let me say it out loud for you, because it's the very question this whole long, gentle night is going to answer. A current that never stops, that needs no push, that flows forever with nothing to keep it going. Isn't that perpetual motion? Isn't that the one thing we're always told is impossible? The dream of the machine that runs forever, the wheel that turns without end, the thing inventors have chased for centuries and never, ever found. We're told again and again that you cannot get something for nothing, that energy can't be made from emptiness, that there's no free lunch anywhere in the cosmos. And yet here is a current in a ring running forever. So which is it? Has someone broken the deepest rule in physics in a quiet laboratory inside a cup of cold metal? Hold on to that question, cradle it, the way you'd hold something small and warm. We are going to walk all the way around it tonight, slowly, and by the end, if you're still with me, and if you're not, that's all right too, you'll see exactly how it resolves. The answer is one of the most satisfying turns in all of physics, and it does not break a single rule. But to reach it properly the way it deserves to be reached, we have to go back to the very beginning. Back to the cold itself, and to the man who first learned how to make it. So let's go back. Way back to the first years of the 20th century, to a city in the Netherlands and to a laboratory that had become, at that time, the coldest place on Earth. The man at the center of it was named Heike Kamerlingh Onnes. He worked at the University of Leiden, and he had spent years, really much of his working life, obsessed with cold. Not cold for its own sake exactly, but with the idea that if you could chill matter down far enough toward the very floor of temperature, you'd find it doing things no one had ever seen. New behavior, hidden behavior, the kind of secrets that only the deepest cold could coax out into the open. Now, to understand what Onnes was up against, you need to know just a little about temperature, and I'll keep it simple and soft. There is a bottom to cold, a true floor. We call it absolute zero, and it sits at minus 273.15 degrees Celsius. That is the coldest anything can possibly be. The point where the ordinary jiggling and trembling of matter, the restless motion that we feel as warmth, would finally come to rest. You can never quite reach it, but you can creep toward it closer and closer, and the closer you get, the stranger the world becomes. Physicists measure these deep colds not in the everyday degrees we use for weather, but in a scale that starts at absolute zero itself. They call its units Kelvin. So 0 Kelvin is that absolute floor, the coldest of all colds. And the temperatures Onnes was chasing were just a handful of Kelvin above that floor, a few small steps up from the absolute bottom of everything. To get there, he needed to do something no one had managed before. He needed to take helium, the same light, airy gas that drifts a party balloon up toward the ceiling, and cool it so thoroughly that it turned from a gas into a liquid. Helium is stubborn about this. It clings to being a gas harder than almost any other substance, refusing to give in until you've stripped away nearly all its warmth. For years it had defeated everyone who tried. And then, in 1908, Onnes did it. In his Leiden laboratory, he cooled helium until it condensed into a clear, faintly shimmering liquid at a temperature of about 4.2 Kelvin. That's around minus 269 degrees Celsius, just 4 small steps above the absolute floor of all cold. It was a triumph. He had made the coldest liquid anyone had ever held, and with it, a tool, a way to chill other things down into that strange, unexplored country near the bottom of temperature. And this matters more than it might first seem, because you cannot go looking for the secrets of the cold until you have first made the cold. You can't study what happens at 4 Kelvin until you have a way to put something there and keep it there. Onnes had built the door. Now he could walk through it. Everything that came after, and everything we're going to talk about tonight, depended on that one achievement first. You have to make the cold before you can find what's hiding in it. So Onnes began to use his liquid helium to chill other materials and to ask a simple-sounding question of them. The question was about resistance. Let me unfold that word gently, because it sits at the heart of everything. When electricity flows through an ordinary metal, through the copper in a wire, say, it does not flow perfectly, freely. The electrons, those tiny carriers of charge, have to push their way through the metal, and as they go, they bump and scatter and jostle against the atoms of the metal itself, which are never sitting perfectly still. Every bump costs a little energy. That energy doesn't vanish, it turns into heat. This is why a wire carrying a lot of current grows warm, why the coils in a toaster glow, why your phone charger gets a little hot to the touch. That bumping, that resistance to the flow, that friction for electricity, physicists call it electrical resistance. And the heat it produces has its own name. We call it Joule heating, after the man who first studied it. In every ordinary conductor, some of the energy you put in is always lost this way, leaking out as warmth, like water seeping out through the walls of a leaky bucket, no matter how carefully you carry it. Now, scientists already knew that cooling a metal lowered its resistance. chill the copper, and the atoms jiggle less, and the electrons bump into them a little less often, and the resistance drops. That much was understood. The interesting question, and the one Ons wanted to answer, was, what happens at the very bottom? As you go down and down toward absolute zero, does the resistance keep falling smoothly, gliding gently toward some small value? Or does something else happen? Nobody knew. No one had ever been able to get a metal cold enough to find out. Ons chose to study mercury. You may know mercury as the heavy silvery liquid that used to sit in old thermometers sliding up and down the glass. He chose it partly because it could be purified to an extraordinary degree, and a pure sample would give a clean, trustworthy measurement with nothing muddying the result. He froze the mercury solid in the deep cold, threaded it so a current could pass through, and began, slowly, to chill it down, watching the resistance all the while, expecting it to slide gently lower and lower as the temperature fell. And then, on the 8th of April in 1911, something happened that no one had predicted and no one was prepared for. As the mercury cooled past about 4.2 Kelvin, right down near the temperature of his liquid helium, its resistance did not slide gently toward some small number. It fell off a cliff. It dropped suddenly and completely to nothing. Not to a little, not to a tiny remainder, to zero as near as any instrument could tell. One moment there was resistance, the ordinary friction of electricity that every metal in the world possesses, and the next, at a temperature just a few degrees above the absolute floor of cold, it was simply gone. Imagine the scene in that laboratory, the careful instruments, the quiet attention, and then a reading that made no sense, that said the electricity was flowing through the mercury without any resistance at all, without losing anything, without the slightest friction. The very first reaction was not wonder, it was suspicion. The reasonable, careful suspicion of good scientists who know that when an instrument tells you something impossible, the instrument is usually wrong. Their first thought was that something had gone awry in the apparatus itself, that perhaps a wire had touched a wire somewhere it shouldn't, a short circuit, a faulty connection that was letting the current slip past the mercury entirely and only making it look as though the resistance had vanished. That would be the ordinary explanation, the sensible one. So they checked, and they checked again. They went back over the apparatus, the connections, the readings, looking for the mistake that had to be there, the loose joint, the accidental shortcut. And they could not find one. The resistance really had vanished. The mercury, below that critical few degrees, truly carried current with no resistance whatsoever. There was no error to find. The impossible reading was simply true. In his laboratory notebook for that day, Ons wrote the result down in his own language, in Dutch, in words that have been quoted ever since. He wrote that the resistance of the mercury was, and here are his words, quick nagenoeg nul. Mercury, practically zero. Such a plain little phrase for such an enormous thing. Practically zero, almost nothing. A quiet line in a notebook, marking the moment a new state of matter first showed its face. Ons needed a name for what he had found, and he settled, before long, on a word that captured the sheer, beyond ordinary nature of it. Above and beyond mere conducting, superconductivity. A metal that conducted electricity not merely well, but perfectly, without resistance, without friction, without loss. It was a word for something that, until that April day, no one had been sure could exist at all. The world of physics took notice. 2 years later, in 1913, Ons was awarded the Nobel Prize in Physics, chiefly for his mastery of the deep cold, for the work that had let him liquefy helium and reach those frozen depths in the first place. And here's a small, telling detail I find rather moving. The prize was given largely for the cold itself, for the technique, for the door he had built into that frozen country. The full meaning of superconductivity, what it actually was, why it happened, what was really going on inside that mercury, was still a mystery. No one understood it. The discovery had arrived decades before the explanation. Ons had found the thing, named the thing, measured the thing, and yet why the thing happened would remain unanswered for nearly half a century more. He'd opened a door into a room no one could yet read the writing on the walls of. Now, as physicists explored further, they learned that this strange vanishing of resistance was not unique to mercury, and it did not happen at just any temperature. Each material that could become a superconductor had its own particular temperature at which the switch flipped, its own threshold below which the resistance disappeared and above which the metal behaved like any ordinary conductor. They gave this threshold a name. They called it the critical temperature. You'll sometimes see it written simply as TC, the C standing for critical. It's the line in the code that the material must cross before its hidden nature awakens. For mercury, the metal where it all began, the critical temperature is about 4.15 Kelvin, right down in the frigid neighborhood of liquid helium, which is why Ons found it exactly where he did, and not before. For lead, the soft grey metal, the critical temperature is a little higher, around 7.2 Kelvin. And among the pure elemental metals at ordinary pressure, the champion, the one that holds out to the highest temperature before surrendering to superconductivity, is niobium, which makes the leap at about 9.3 Kelvin. Still desperately cold, mind you, still only 9 small steps above the absolute floor of everything, but the highest of the simple metals all the same. I want to pause here and let you feel just how cold these temperatures truly are, because it matters for everything that comes later. 9 Kelvin, 7 Kelvin, 4 Kelvin. These are not winter temperatures. These are not even the temperatures of the polar ice. These are colds so profound that the only way to reach them in those early days was to bathe the metal in liquid helium, that hard-won, shimmering liquid that Onnes had fought for years to make. The superconductors of that era could only live in the embrace of the very coldest substance human beings knew how to produce. The cold was not incidental. The cold was the price of admission. And later tonight, when we come to understand why the cold matters so deeply, why warmth, even a little of it, destroys the whole delicate effect, you'll see that this isn't just a practical inconvenience. It's woven into the very heart of how superconductivity works at all. But let me come back now to that word, zero. Zero resistance. Because I don't think we've yet let it be as astonishing as it really is, and I want you to feel the full weight of it as you lie there in the quiet. When we say a material has very low resistance, we usually mean it's a good conductor. Copper is a good conductor, silver even better. We string our cities together with copper precisely because it lets electricity flow through it so freely, with so little loss. But so little loss is not no loss. Even the finest copper, even the purest silver, still has some resistance. Still bleeds away a little energy as heat with every passing moment of current. Run a current through a loop of copper and stop pushing, and that current dies in a heartbeat, a tiny fraction of a second, its energy spent as warmth, leaking out through the resistance like water through that leaky bucket, until there's nothing left and the loop falls still. Zero resistance is something else entirely, different not in degree but in kind. In a superconductor, there is no leak. The bucket has no holes at all. A current set flowing in a superconducting loop produces no Joule heating. None, because there's no friction for it to push against, no bumping of electrons against atoms, no energy bleeding away into warmth. And so it does not die, it cannot die because there is nothing draining it. It simply continues around and around undiminished for as long as the cold holds. and the material stays below its critical temperature. And now you can see, can't you, how we arrive back at that ring from the very beginning of tonight, the ring of cold metal with its current that never stops. That undecaying current isn't a separate marvel off on its own. It's the most direct, most vivid expression of what zero resistance truly means. No resistance, no loss, no decay. No decay, and the current flows on and on, longer than 100,000 years, longer, if the calculations are right, than the universe itself has yet existed. So we have the phenomenon now laid out plainly, a current that flows forever in a ring of cold metal, because the metal, below a few degrees above absolute zero, has surrendered all its resistance and lets the electricity circle without any friction at all. We have the man who found it, Ons, in his Leiden laboratory with his hard-won liquid helium and his pure mercury on that April day in 1911, writing practically zero in his notebook and reaching perhaps for the word superconductivity without yet knowing what lay beneath it. And we still have, sitting unanswered in the dark with us, that quiet objection from the back of the mind. A current with no push, running forever. How on earth is that not perpetual motion? How is that not the impossible thing we've always been told can never be? We've described what happens. We have not yet touched why. And the why is where the real strangeness lives. The part that takes us down beneath the metal, beneath the flowing current, into the world of the electrons themselves, where two particles that ought to repel one another somehow become partners, and millions upon millions of them fall into a single, shared step, like an entire ballroom of dancers moving as one. That's where we're going next. Slowly, gently, when you're ready. There's no rush. The current has been flowing for longer than we can measure, and it will still be flowing when we get there. But before we go down there, let me sit with you a moment longer at the surface, where the picture is still simple and warm, because there's a temptation worth resisting. The temptation is to think that a superconductor is just a very, very good metal. A better copper, a wire with the resistance turned down so low, it might as well be nothing. And honestly, that's where a lot of people stop. And it sounds reasonable, doesn't it? Copper is a fine conductor. Silver is better. Surely if you keep climbing that ladder, you arrive eventually at something that conducts so well the current barely fades. And that's your forever current, and there's nothing mysterious about it at all. But that isn't what's happening here. Not even close. And the gap between a really good conductor and a superconductor is not a small gap of degree. It's a gap of kind. It's the difference between a hill and a cliff. Let me show you why with copper itself, since we've already invited it into the room. Take a ring of ordinary copper, cool it down, set a current spinning in it, and then step back and watch. The current will die, not in 100,000 years, not in a year. It will collapse in a fraction of a second. Gone almost before you finish setting it going, because copper, good as it is, still resists. Every electron drifting through it is forever bumping into the jostling atoms of the metal, scattering off them, losing a little energy with each collision, and all that lost energy turns into heat. We have a name for that: Joule heating. It's the same warmth you feel in a phone charger, the same glow in the coil of a toaster, the same reason a wire carrying too much current gets hot. The current pays a tax to flow, and the tax is heat, and in a closed loop with nothing pushing, that tax drains the whole account in an instant. So that's the ordinary world, the world where everything fades, where motion costs something, where a current with no battery behind it is a candle already guttering out. Now hold that picture next to the other one. The ring of mercury or lead or niobium cooled below its own particular threshold. Set the current spinning there and there is no tax, none. the electrons circle and circle and nothing turns into heat because nothing is lost, because there is no friction to lose it to. Zero resistance isn't very small resistance. It is genuinely, measurably zero, as far as any experiment has ever been able to reach down and check. And with no heat draining the loop, there is simply nothing to stop the current. It isn't fighting to keep going, it just goes because going is the easiest thing in the world when nothing pulls against you. That word, zero, deserves a moment of its own because we use it loosely in everyday life. I have zero patience left. There's zero chance. We rarely mean it exactly, but here it is, meant exactly. And that exactness is the whole strange heart of the thing. The resistance does not shrink towards zero as you cool the metal, the way you might expect, sliding down a gentle slope. It does something stranger. It falls and falls, behaving more or less like an ordinary metal getting better at its job, and then at one particular temperature, it doesn't ease the rest of the way down. It drops, abruptly, off the cliff, from a small number to nothing at all at once, as though the metal crossed a line and became a different substance on the other side of it. That temperature has a name, and you'll hear it often tonight, so let it settle in gently now. It's called the critical temperature. Physicists write it as Tc, just a T with a little c, for critical. And every superconductor has its own. It's the doorway. Above it, the metal is ordinary, resisting, taxing every current with heat, just like the copper. Below it, the metal has crossed over into the superconducting state, and the tax is gone. And these doorways sit shockingly low. For Mercury, on is Mercury, the very first one ever found. The critical temperature is about 4.15 Kelvin, 4 degrees above absolute zero, colder than the deep of space between the stars. For lead, it's a touch warmer, around 7.2 Kelvin. For niobium, which holds the record among the pure elemental metals you could pick up and hold at ordinary pressure, it's about 9.3 Kelvin, still desperately, profoundly cold. Still a place you can only reach with liquid helium and a great deal of patience. You can hear in those small numbers why Ons had to make the cold before he could find the secret hiding inside it. There was no shortcut. You cannot stumble upon superconductivity by accident at room temperature, leaving a wire on a bench. It only shows itself down in that thin band just above the coldest possible cold, in a place nature almost never goes on its own. He spent years learning to liquefy helium precisely because that was the only key that could open the door to 4 Kelvin. And only once the door was open could the phenomenon waiting on the other side of it step out and be seen. So picture the two rings again, side by side, as you drift. The copper one, where the current is already dying, already surrendering its motion to heat, fading the way everything in the ordinary world fades. And beside it, the cold one, where the current simply continues, indifferent, unpushed, untaxed, circling in the dark for longer than the stars have burned. Same metal in spirit, same electrons, same loop, and yet two utterly different fates, separated by nothing but a handful of degrees and the crossing of one invisible line. That's the cliff. That's the difference of kind, not degree. A superconductor is not a better conductor, it is something else entirely. A genuinely different state of matter, the way ice is something else entirely from cold water, even though both are only H2O, cross the line and the rules change. And here's the thing that should keep tugging quietly at you as you sink towards sleep. We've now said what no resistance means, and we've said it firmly on no heat, no tax, no draining away. But we still haven't said why. We've described the cliff without explaining what holds the climber up on the other side of it. Why should scattering simply stop? Why should the electrons, which in copper are forever colliding and losing their way, in this cold metal glide on as though the obstacles had vanished. What changed down among the particles when the metal crossed its critical line? That answer is waiting just below us now, in the world of the electrons themselves. In those improbable partnerships I mentioned, the two particles that ought to push each other away and instead reach for one another across the cold lattice of the metal. So here is where the story makes a deeper turn. Because to understand why the current truly, literally never stops, we have to go down into the metal itself, past the level of wire and loop and laboratory bench, all the way down to the individual electron, that tiny carrier of charge that in ordinary copper stumbles and stops and gives its momentum away as warmth. We have to understand what happens to the electron when the temperature drops below the critical line. And the answer, which took the better part of half a century to fully work out, is both precise and strange in exactly the way that physics at its best tends to be. The theory arrived in 1957. 3 names are attached to it: John Bardeen, Leon Cooper, and John Robert Schrieffer. And already there is something worth pausing on, because John Bardeen is a name that carries a particular distinction in the history of science. In 1956, the year before the paper on superconductivity, Bardeen had shared the Nobel Prize in Physics for the invention of the transistor, the device that eventually became the foundation of every piece of modern electronics, every computer, every phone, every circuit that processes information anywhere in the world. That alone would have been enough for one career, more than enough for one life. And yet there he was, the very next year, sharing authorship of an explanation for one of the deepest unsolved mysteries in physics. When the Nobel Committee returned in 1972 to award the prize for superconductivity to Bardeen and Cooper and Schrieffer, it was Bardeen's second Nobel Prize in physics, a distinction no other person in history has held. 2 prizes in the same field for 2 completely different discoveries. It is, quietly, one of the most extraordinary scientific biographies of the 20th century. The theory they published goes by the initials of their surnames, BCS, and what BCS theory explained, what it built up from first principles, from the known behavior of electrons and the quantum rules they obey, was why certain metals, when cooled below a critical temperature, allow electrons to pair up and condense into a collective state that is protected from all the ordinary disturbances that would scatter them. Let me build this slowly, because each step matters and none of them is difficult if taken one at a time. Start with the electron in a normal metal, in copper, say, or silver, any ordinary conductor at room temperature. An electron moving through the metal is not moving through empty space. It is moving through a crystal lattice, an orderly 3-dimensional scaffold of positive ions, the metal's atoms stripped of their outermost electrons, sitting in regular positions, vibrating gently because they are warm. The free electrons, the conduction electrons, drift through this scaffold when you apply a voltage, and as they drift, they collide. They hit the vibrating ions. They scatter off impurities, small defects in the lattice, places where the crystal is not quite perfect. Each collision knocks the electron slightly off its intended path, transfers a little of its energy to the lattice, and that transferred energy becomes heat. That is resistance. That is Joule heating. That is why your phone's charging cable grows warm, why power lines lose energy across long distances, why every ordinary conductor in the ordinary world taxes every current that passes through it. Now cool the metal down. As the temperature falls, the ions vibrate less. There are fewer thermal fluctuations to scatter the electrons. The resistance decreases gradually, gently, as you'd expect it to. This happens in copper too, and in every metal. Cooling improves conductivity, reduces scattering. And so if superconductivity were just the end point of that curve, if it were just a very, very good conductor where scattering had become vanishingly rare, you might expect a smooth approach to zero, a gentle asymptote. What you do not expect is an abrupt cliff, a sharp, transition at a specific temperature, where the resistance does not approach zero gradually, but drops to it completely, instantaneously, as though a switch were thrown. That abruptness is the sign that something qualitatively different has happened. The system has crossed a phase transition, like water turning to ice, not gradually becoming more solid, but changing state at a definite temperature. And what has changed at the microscopic level is that the electrons have started doing something they would never do under ordinary circumstances. They have started pairing up. This is the Cooper pair, named for Leon Cooper, who in 1956, before the full BCS paper, worked out the mathematical demonstration that two electrons near a metal's Fermi surface, the sea of filled quantum states that defines how electrons organize themselves in a metal, could form a bound pair with a lower energy than two isolated electrons, no matter how weak the attractive force between them. And the force between them, improbable as it sounds, is attractive, mediated not directly between the electrons themselves, which repel each other, as electrons always do, but through the lattice of positive ions they move through. Here is the picture, and it helps to close your eyes a little, let it build. An electron moves through the metal. It carries a negative charge. The positive ions of the lattice are attracted to it, and as it passes, they lean toward it slightly, collectively, a faint bow of the crystal toward the charge moving through it. This happens fast, but not instantaneously. The ions are much heavier than the electron, many thousands of times heavier, and they respond sluggishly. So the electron moves on ahead of the distortion it has created. Behind it, for a brief moment, the lattice is still leaning inward, still showing a small, transient surplus of positive influence in the region the first electron has just passed through. A dimple in the crystal, if you like, a soft hollow left behind in the otherwise neutral lattice, and a second electron moving through that same region a moment later feels that faint, positive excess. It is drawn toward it, not toward the first electron. The first electron is already far away, insulated by distance, but toward the temporary positional distortion the first electron caused. The two electrons have never come face to face. They have communicated only through the lattice they both move through, the way two ships on the ocean might respond to the same wave without ever seeing one another. The quantized vibrations of this lattice are called phonons. The BCS picture is one where Cooper pairs are bound together through the exchange of phonons, lattice vibrations carrying the attraction. You can think of it as the first electron sends a message through the lattice in the form of a distortion, and the second electron receives it, drawn toward the region of transient positive charge. It is an indirect attraction, fragile and easily broken, which is why the cold matters so much. At higher temperatures, thermal vibrations of the lattice overwhelm the delicate signal, the dimple is blurred by noise, and the attraction is lost. But in the cold, below the critical temperature, the phonon-mediated attraction is just strong enough, and the pair holds together. Now here is where the quantum mechanics enters, and it changes everything. Electrons individually are fermions. This is a fundamental classification of all the particles in nature. They divide into two families, fermions and bosons, depending on a property called spin, which is a kind of intrinsic angular momentum. Fermions have half-integer spin to 1/2, 3/2, and so on. Bosons have integer spin 0, 1, 2. And the difference between these two families is not merely mathematical, it is a deep, consequential difference in how they are allowed to organize themselves. Fermions obey the Pauli exclusion principle. No two fermions can occupy the same quantum state. This is the rule that prevents all the electrons in an atom from collapsing into the lowest energy level, the rule that builds the whole structure of the periodic table, the rule that gives matter its solidity and chemistry its variety. Without the Pauli exclusion principle, electrons would all pile into the same ground state, atoms would all look identical, There would be no chemistry, no biology, no solid matter as we know it. The exclusion principle is one of the architectural principles of the universe. Bosons are not governed by this rule. Bosons can occupy the same quantum state in arbitrary numbers. In fact, they actively tend to pile into the same state. There is a statistical preference for bosons to crowd together. This is what light does in a laser, all the photons lining up in the same state, which is why the beam is coherent. It is what happens in a Bose-Einstein condensate, a strange state of matter in which a large collection of bosonic atoms drops to the same quantum ground state and begins to behave as a single, unified quantum object. A Cooper pair consists of 2 electrons. Each electron has spin 1/2. When the 2 electrons pair up, their spins can combine in a way that gives the pair a total spin of 0. An integer and an object with integer spin behaves collectively as a boson. The pair is not an electron anymore in the sense that matters for statistics. It is a compound object that follows the rules of bosons. This is the pivot on which everything turns. Below the critical temperature, the Cooper pairs do not just form, they condense. In the same way that a Bose-Einstein condensate drops all its particles into the same ground state, the enormous number of Cooper pairs in a superconductor, we are talking about numbers on the order of trillions upon trillions, 1 pair for every pair of electrons that participates, all collapse into a single shared quantum state. Not approximately the same state, not a very similar state. The same state, mathematically, a single quantum mechanical wave function that describes all of them at once. This is what physicists call the macroscopic wave function, and it is one of the stranger objects in all of physics. A wave function is normally a description of a single particle, or a few particles, something so small and fragile that a stray photon from a laboratory instrument can disturb it beyond recovery. Normally, quantum behavior at this level is ruthlessly hidden from the human scale by the sheer statistical noise of having enormous numbers of particles, all in slightly different states, all washing out each other's quantum nature into the smooth, predictable world of classical physics that we inhabit. But in a superconductor, the quantum state doesn't wash out. It becomes the macroscopic state. The whole condensate, a chunk of metal sitting on a laboratory bench that you could pick up and weigh, is described by a single wave function. The quantum world has leaked into the human world, and that is extraordinary. Now comes the reason resistance vanishes. And this part, I think, is the most satisfying logical step in the whole story. In a normal metal, resistance comes from scattering. An electron moving through the lattice hits something, an ion, an impurity, a thermal vibration, and its momentum is deflected, absorbed, converted to heat. The whole flow of current is a statistical average over trillions of these individual collision events, each one nudging an electron off course, each one taxing the current a little. In the superconductor, for a collision to scatter one of the paired electrons, it would have to knock that electron out of the shared quantum state that all the pairs occupy together. But the pairs are not independent objects, each in their own private state. They are all part of the same collective state, the macroscopic wave function. To scatter one pair, you would to change its momentum. To knock it out of the condensate, you would have to change the state of the entire condensate, all of it at once. Think of it this way. Imagine trying to deflect a single marble from a tight formation of a trillion marbles, all locked together, all moving as one. You nudge one marble at the edge, and the whole mass nudges with it. You cannot single out just one and change only its path, because it has no individual path. It shares the path of the whole. To change the current, you would have to change the quantum state of the entire macroscopic wave function simultaneously, and the energy required to do that is far, far greater than anything a stray thermal vibration or a small defect in the crystal can supply. This is why resistance is not merely reduced, it is gone completely. The mechanism by which resistance exists in a normal metal, individual electron scattering, is simply not available. It is not that collisions happen less often. It is that the kind of scattering that drains current cannot happen to the condensate without changing the whole condensate, and the quiet, low-energy cold of the laboratory provides nothing like enough energy to do that. The current is protected by the quantum nature of the state itself, by the fact that there is no such thing as a single pair to deflect, only the one great collective, indivisible and unperturbed. This is the answer to the question of why resistance vanishes. It is not that the obstacles have gone away, the lattice is still there, the impurities are still there, the crystal is still imperfect, the electrons are still moving through all of that, but they are no longer moving as individuals, they are moving as a single quantum state, and the single quantum state is protected. But there is more to this protection, and it is worth going one step further before we leave the mechanism, because the next piece is what gives the persistent current its astonishing staying power, what sets the lower bound on its decay time at figures that exceed 100,000 years, and, in theoretical terms, vastly longer than the age of the universe. The condensate of paired electrons does not just float in a featureless quantum state, it has a characteristic energy. And here is the crucial point. There is a gap, an energy gap, between the energy of the superconducting ground state and the lowest possible energy of any state that does not have the pairing. A minimum energy that must be supplied before a Cooper pair can be broken up into two independent electrons, two ordinary quasi-particles. For conventional superconductors of the kind Onnes first studied, this gap is small, on the order of milli-electron volts, thousands of times smaller than the energy of visible light. But at the temperatures where these superconductors live, below 4 or 7 or 9 Kelvin, the average thermal energy available from the ambient vibrations of the lattice is smaller still. The key is there, the energy to break a pair, but the cold cannot supply it. Think of a locked door. The lock is not very strong. A determined force could open it easily, but the only forces available at this temperature are timid, gentle, insufficient. They rattle the handle and find it firm. They cannot pay the price of admission. The pairs remain intact, the condensate remains whole, and the current flows on. This is why the cold is essential. It is not merely a practical requirement, a matter of keeping the metal in the right phase the way you might keep butter cold to keep it solid. It is a physical necessity. The energy gap that protects the pairs from breaking is itself fragile. Warm the metal and you increase the thermal energy available. At temperatures well below Tc, the gap is wide relative to what the heat can offer and the pairs are safe. As the temperature rises toward Tc, the gap narrows because the pairing interaction weakens as the lattice vibrations grow more energetic and begin to disrupt the delicate phonon-mediated attraction. And at Tc, the gap closes entirely. The pairs can no longer form. The condensate dissolves. The macroscopic wave function fragments back into trillions of independent electrons, each going its own way, each subject to the ordinary collisions and scatterings of a normal metal, and resistance snaps back on in an instant. Warmth supplies the key that fits the lock, and the door opens, and the current dies. There is a word for the independent electrons that live in the gap's absence, or that can be created very rarely inside a superconductor if enough energy is supplied locally to break a pair. Physicists call them quasi-particles. They are not exactly free electrons because the superconductor's environment modifies their behavior in subtle ways. But they behave like electrons in the sense that matters for resistance. They scatter, they lose energy, they carry the ordinary burden of the normal state. When the temperature is well below Tc, there are very few quasi-particles. The gap is too wide, the thermal energy too small to break many pairs. As Tc is approached, More and more pairs are broken, more quasi-particles appear. The gap shrinks and the condensate weakens. The transition is a balance between the pairing force trying to hold electrons together and the thermal energy trying to drive them apart. At Tc, the thermal energy wins. So we have now the full picture of the mechanism at its heart. The electrons pair up through the lattice, indirectly, through phonons, the lattice distortion. One electron leaves behind, drawing the next one in. The pairs behave as bosons and condense into a shared quantum state. The shared quantum state cannot be disrupted by the small scatterings that produce resistance in normal metals. An energy gap protects the pairs from being broken by the low thermal energy available at these temperatures, and the current, once set, flowing in a closed loop, simply has no mechanism to decay. It is not fighting against something and winning. It is in a state where the fighting cannot begin. And here, just for a moment, I want to return to the question that has been waiting since the very beginning of this journey. The one that ought to be sitting in the back of your mind even now, even as sleep presses in at the edges. Because we have said that a current can flow forever, that its decay time exceeds the age of the universe, that it is protected by quantum mechanics and the energy gap and the shared wave function. But the phrase should still itch a little. A current that flows forever, without any energy being added, without anything pushing it. That sounds uncomfortably like a perpetual motion machine. And it is worth saying, clearly and carefully, why it is not. A perpetual motion machine, in the sense that thermodynamics forbids, is a machine that does work continuously without any energy input. It is a machine that violates conservation of energy, one that creates something from nothing. The reason such a machine is impossible is that every process in nature has some inefficiency, some path by which energy leaks away as heat or radiation or mechanical vibration, and a truly perpetual machine would require plugging every one of those leaks forever, which cannot be done. But the persistent current in a superconducting ring does no work. It circulates in a closed loop. It generates a magnetic field. We will come to that field very shortly. But it does not deliver energy anywhere. Nothing is extracted from it. No lamp lights up, no motor turns, no useful output comes from the circulating current beyond the field it maintains. The moment you tried to draw power from it, to connect a resistor to the ring and extract the energy of the circulating current, you would break the superconducting state, or you would simply find that the current dies as it does work, exactly as thermodynamics requires. The persistent current is not a source of free energy. It is energy stored in a magnetic field, and that stored energy simply does not dissipate because the medium it is stored in, the superconducting condensate, has no dissipative mechanism available to it while it remains cold and intact. It is like asking why a frictionless pendulum swings forever. In a world without friction and air resistance, a pendulum would indeed swing forever. Not because energy is being created, but because none is being lost. The persistent current is the electromagnetic analog of the frictionless pendulum, a system in which the usual dissipation mechanism has been, by a quantum trick, completely removed. This is the distinction between perpetual motion of the first kind, forbidden, impossible, energy created from nothing, and simply a state of affairs where no energy is lost because no mechanism for loss is available. The superconductor is the latter. It is not magic. It is mechanics without friction, maintained by the deep architecture of quantum states, and it is cold, necessarily, profoundly, specifically cold. The cold is not an inconvenience or a limitation to be engineered around. The cold is the condition of existence for the whole phenomenon. Without it, the pairs break, the condensate dissolves, the protection vanishes, and the current dies. Which is, in its own way, a kind of wonder that the universe permits this state at all, that there is a temperature low enough and materials that can reach it, and a quantum rule that then locks in a current that time cannot touch is not obvious. It did not have to be this way. The universe did not have to include phonon-mediated pairing as a possibility, or the condensation of bosonic pairs, or the energy gap, or any of it. But it does. And Ons found the edge of that possibility in Leiden in 1911 with a tube of mercury and a bath of liquid helium, and the resistance dropped to zero, and for a moment no one quite believed it. Let the mechanism settle now, the way something settles when you have understood it well enough. The Cooper pair. The unlikely partnership across the lattice. Two electrons who never meet, but who are nonetheless bound by the ghost of the crystal between them. The condensate, the vast, silent gathering of pairs into a single quantum state, one wave function for the whole, indivisible. The energy gap, the locked door, that thermal noise at these temperatures cannot open, the protection that keeps the pairs intact, and the condensate whole. And from all of this, the current that circulates without spending anything, without draining, without the ordinary tax that every conductor in the warm world must pay. There is something almost restful about it when you hold the picture clearly. In the warm world, everything is always losing something: heat to the air, energy to friction, momentum to collisions. The second law of thermodynamics is the great accountant, always taking its cut. But down here, in the cold of the laboratory, below the critical line, the quantum mechanic steps in front of the accountant and says, "Not here, not to this." The cut cannot be taken from a state that the accounting cannot reach. The current circles and circles and circles, and out there in the world above the cold, in the laboratory where Bardeen and Cooper and Schrieffer were working in the 1950s, there had been 46 years of knowing that the phenomenon existed. 46 years since On watched the mercury's resistance drop and reached for the word practically zero, without understanding why. The floating magnet had been demonstrated, the critical temperatures had been catalogued for many metals, the zero resistance had been measured and verified again, but the mechanism, the deep reason, had remained opaque through all of it, resistant to the standard tools of theoretical physics. BCS theory cracked it, and it did so by taking seriously the idea that the electrons in the metal were not isolated individuals but participants in a collective quantum state, that the right question was not what happens to one electron, but what quantum state the whole system prefers at low temperature in the presence of even a weak, attractive interaction. And the answer was pairing, condensation, protection, all of it following inexorably from the mathematical properties of fermions, bosons, and the Fermi surface. It is a theory that fits experiment beautifully for the metals and alloys it was designed to explain. The predicted energy gaps match measured values. The predicted transition temperatures calculated from the strength of the phonon coupling match the observed critical temperatures. The predicted factor in the flux quantum, the 2e in the denominator, was confirmed experimentally in 1961, as we will come to. The theory is, for conventional superconductors, one of the great successes of 20th century physics, and Bardeen, standing at the ceremony in Stockholm in 1972 to accept his second Nobel Prize in Physics, the only person ever to do so in the same field, must have felt some particular quality of completeness. The transistor in 1956, the mechanism of superconductivity in 1972. Two windows opened onto the quantum world, each of enormous consequence, each the work of collaboration and persistence and mathematical clarity. Physics at its best. But let us not get too comfortable in the theory, because there is still something we have not yet accounted for, a piece of the puzzle that BCS tells us must exist, but that has not yet appeared in the story of this cold ring and its forever current. We have established that resistance vanishes. We have established why. We have established that the current, once set moving in the loop, persists because the mechanism of its decay has been removed, but we have not yet asked, and the asking matters, what happens to the magnetic field? Because the current in the ring is a loop of moving charge, and any moving charge generates a magnetic field. The current circulating in the ring threads a magnetic flux through the center of the ring, a flux that is the fingerprint of the current proportional to it, changing only if the current changes. And we have said the current does not change, which means the flux does not change, which means the field through the ring is locked in. But there is more than locking. There is something stranger, something that BCS theory predicts and that experiment has verified with a precision that leaves no room for doubt. The field through the ring cannot take just any value. It is quantized. It can only exist in exact, discrete multiples of a single tiny number. And that number, the magnetic flux, quantum, carries encoded within it the most direct proof that the charge carriers in a superconductor are not single electrons, but pairs. That is the next part of the story, and it waits just ahead, as quiet and exact as the cold metal itself. But for now, stay here a moment. Let the electrons pair up in the lattice, feel the dimple closing behind the first and drawing in the second. Let the pairs condense millions upon millions into one state. Let the current flow on, protected by the gap, indivisible by the rules of the quantum, circling in the dark of the cryostat, colder than almost anywhere in the observable universe. You understand now why it flows, the rest, the field, the flux, the locked coins of magnetism, the floating magnet, the visible proof of the invisible rule. All of that grows naturally from here. And there is no rush. The current will still be flowing when you wake. And here is where the story takes a turn toward the visible. Everything we have spoken about so far has been hidden. The Cooper pairs live inside the metal, invisible and indistinguishably woven into the quantum condensate. The macroscopic wave function extends through the whole superconductor like a field of influence no eye can register. The energy gap sits at the scale of millielectron volts, which is a scale so small you could line up 1,000,000 of them and they still would not amount to anything you could hold in your hand. The current circles in the ring, and from the outside it looks like nothing at all. Just a metal ring sitting in the cold, in the quiet, producing no light, no sound, no obvious sign that anything extraordinary is happening inside it. But there is a way to make the invisible visible. There is a sign, a physical signature, that the superconducting state prints onto the space around it, a sign that Walter Meissner and his colleague Robert Oxenfeld found in 1933, in the years before anyone had a real theory to explain what they were looking at. And the sign is this: the magnetic field disappears. Not from the universe, not from existence, just from the interior of the superconductor. The superconductor pushes it out. Let me take a moment with that because it is easy to pass over it too quickly and miss how strange it is. If you take an ordinary piece of metal, say a block of copper or a rod of iron, and you place it in a magnetic field, the field passes through it. Some metals distort the field slightly, some concentrate it, some are barely affected at all, but the field goes in, it fills the interior. A superconductor does something categorically different. Cool it below its critical temperature, and the magnetic field is expelled from its interior. The field cannot get in, it is pushed out to the surface, and then beyond the surface, into the air around the material. The inside of the superconductor becomes a region where, as far as magnetic fields are concerned, nothing exists. This is called the Meissner effect. It is one of the defining properties of the superconducting state, and it is, in a sense, the most important discovery that separates superconductors from everything we thought we understood about electricity and magnetism before 1933. Let me explain why. Before the Meissner effect was discovered, physicists knew that a perfect conductor, a hypothetical material with truly zero resistance, would have interesting magnetic properties. If you cooled a material to perfect conductivity while it sat in a magnetic field, the field would freeze in place inside it. The idea is that in a perfect conductor, any change in magnetic flux through the material would induce a current to oppose that change, and because the resistance is zero, that induced current would flow forever and would perfectly cancel any change. So the field would be locked. Whatever field was present when the material became perfectly conducting would be trapped inside, preserved, unable to change. That sounds almost like the Meissner effect, but it is not. It is crucially, fundamentally different. A perfect conductor traps whatever field is there. A superconductor expels the field entirely, regardless of the history. Here is a way to feel that difference. Imagine you have a block of some hypothetical perfect conductor sitting in a region with no magnetic field. You cool it to perfect conductivity. Then you bring a magnet close. In a perfect conductor, the induced currents would oppose the change and keep the field out. So it would look like expulsion. Good. Now imagine the reverse. You start with the material in a magnetic field, cool it to perfect conductivity, and then remove the magnet. In a perfect conductor, the field would be trapped inside because changing it would require changing the flux, which would require overcoming the induced currents. The field stays. In a real superconductor, both scenarios give the same result. Cool it below Tc in any field, and the field is expelled. The history does not matter. The Meissner effect is active. The superconductor does not passively trap whatever was there. It actively pushes the field out. That word, actively, is important. The Meissner effect is not just a consequence of zero resistance. It is a separate, independent property of the superconducting state. It means that a superconductor is not merely a metal with the resistance turned off. It is a new state of matter with its own distinct relationship to the magnetic field around it. Physicists call this property perfect diamagnetism. The superconductor creates currents in its surface that precisely cancel any magnetic field trying to enter, expelling it completely. And that, finally, is what makes the magnet float. You have probably seen the demonstration. A small magnet, sometimes a little disc, sometimes a cube of rare earth magnetic material, is placed above a flat piece of superconductor that has been cooled in liquid nitrogen. And the magnet lifts. It hovers in the air above the cold surface, motionless, with nothing touching it from below, nothing connecting it to the ceiling, just floating. It floats because the superconductor is expelling the magnetic field. The magnet's field tries to penetrate the surface of the superconductor, and the surface responds with currents that produce an equal and opposite field, pushing back. The magnet finds itself sitting on a cushion of its own reflected field. The equilibrium is stable. If the magnet dips toward the surface, the expulsion strengthens and pushes it back. If it rises, the repulsion weakens and it sinks back. It finds its level and holds it. This is not a trick. It is not wire or string or some cleverly hidden mechanism. It is quantum mechanics expressed at the scale of a magnet you can hold between your fingers. And here is the thing to carry into sleep with you. The magnet floats because the field is pushed out, not because it is trapped. The Meissner effect is not a trapping, it is an expulsion. That is the signature of a true superconductor. That is the proof, visible to your own eyes, that something categorically new is happening inside the cold metal below. Now, the field is expelled from the interior, but not from everything, not from every atom of the material, down to its very center. The magnetic field does not simply stop at the surface and retreat. It does something more subtle. It penetrates a little. It seeps in across a thin layer at the surface, a layer just tens to hundreds of nanometers thick, and then it decays exponentially, quickly, to zero in the interior. This thin layer has a name. It is called the London penetration depth, and it was described mathematically by two brothers, Fritz London and Heinz London, in 1935, in a pair of equations that now carry their name, the London equations. Fritz and Heinz London were physicists who had fled Germany and were working in England. They were attempting something bold, to write down the simplest possible mathematical description of a superconductor's electromagnetic behavior, not from a microscopic theory. There was no microscopic theory yet that would take 2 more decades and John Bardeen and his collaborators, but from the observed facts, from the zero resistance, from the Meissner expulsion. They said, what equations would a material have to obey if it exhibited exactly these properties? And they wrote them. The London equations are not the full story. They do not tell you why the superconductor behaves this way. They are phenomenological. They describe the behavior without explaining its origin. But they describe it correctly and quantitatively. And one of the things they predict is the penetration depth. The magnetic field falls off exponentially as you move inward from the surface, with a characteristic length scale that is material dependent, but typically in the range of tens to a few hundred nanometers for most conventional superconductors. A nanometer is 1/1000th of a meter. A human hair is about 80,000 nanometers across, so the penetration depth at the skin of magnetic field at the surface of a superconductor is a layer so thin that you could stack tens of thousands of them and not reach the thickness of a single strand of hair. The field lives only in that ghostly thin rind. Below it, inside the bulk of the material, the field is zero. The metal has sealed its interior against the magnetic world outside. This is the London penetration depth, and it is one of the fundamental parameters that characterize a superconductor. Different materials have different values. The depth depends on the density of superfluid electrons, which depends on temperature and on the material itself. As the temperature rises toward Tc and the superconducting order weakens, the penetration depth grows. The field seeps in more deeply. At Tc, the penetration depth formally diverges, the field penetrates everywhere, and the material is no longer superconducting. So the Meissner effect gives you the floating magnet, the expelled field, the thin London skin at the surface where the field still lives before it is cancelled to nothing. And the London equations give you the mathematics to describe all of that with precision, 2 decades before anyone understood why the equations were right. But now, let us go further. Because there is something even stranger hiding in all of this, something that connects the expelled field to the circling current in the ring, something that brings us to one of the most beautiful and precise experimental facts in all of condensed matter physics: the magnetic flux through a superconducting ring. We have already said that once a current is set flowing in a closed superconducting loop, a ring of cold metal circling, it does not stop. The field threading the center of the ring, the flux through the hole in the ring, is locked by this current. As long as the current flows, the flux is there. As long as the metal is below Tc, the current flows. As long as the flux is there, the current flows. The two are locked together in a self-reinforcing embrace. But there is a constraint on the flux that is more fundamental than any of it. A constraint that does not come from the persistence of the current, but from the nature of the superconducting quantum state itself. The magnetic flux threading the ring can only take specific discrete values, not just any value, not a continuous range, specific, discrete, quantized. The flux through a superconducting ring must be an exact integer, multiple of a single fundamental unit. That unit is called the magnetic flux quantum, and it is given the symbol F0, capital Phi, subscript 0. Its value is h divided by 2e, where h is Planck's constant, and e is the electric charge of a single electron. In numbers, Fe0 is approximately 2.07 times 10 to the negative 15 Webers, 2,000ths of a trillionth of a Weber, an extraordinarily small number. The flux through the ring must be 0, or Fe0, or 2 Fe0, or 3 Fe0, or any non-negative integer times Fe0, but nothing in between. The metal cannot hold 1.5 flux quanta. It cannot hold pi flux quanta. It counts its magnetism in indivisible coins, and the coins have a fixed denomination. Let me give you an image for this. Think of water flowing into a bucket. Normally, you can put in any amount of water, a little, a lot, a precise number of milliliters, or something between any two numbers you care to name. Water is continuous, but now imagine that the bucket only accepts water in whole cups. You can have 0 cups, 1 cup, 2 cups, 3 cups. You cannot have half a cup, or a cup and a third, or any amount that is not exactly a whole number of cups. If you try to pour in half a cup, the bucket simply refuses. That is, in a very loose way, what is happening with the magnetic flux in a superconducting ring. The ring can hold 0 units of flux, or 1, or 2, or 3, not a fraction. The magnetic field through the ring is discretized, broken into fixed, indivisible units by the quantum mechanics of the superconducting state. Why? Why does this happen? The answer goes back to the macroscopic wave function, the single quantum state that describes all the Cooper pairs in the ring together. A wave function has a phase. It oscillates in a mathematical sense as you move around the ring. And for the wave function to be physically consistent, to be single-valued, meaning it gives the same answer whether you go all the way around the ring once or twice or 10 times, because there is only one answer at each point. The phase must return to itself after each complete circuit around the ring. This is a topological constraint. A topological constraint is one that you cannot escape by making small changes, and it is locked in by the global shape of the situation, not by the local details. The wave function must be consistent when it comes back around, and the only way to satisfy this consistency is for the total phase change around the loop to be an integer multiple of 2 pi. No fractions, no irrational numbers, just whole multiples. And it turns out that the magnetic flux through the loop is tied through the equations of quantum mechanics to exactly this phase change. The flux and the phase are linked. Fix the constraint on the phase must be whole multiples of 2 pi, and you automatically fix the constraint on the flux must be whole multiples of 0. The quantization of flux is not imposed from outside. It grows directly from the requirement that the quantum state describing the superconductor be mathematically self-consistent. The ring imposes it on itself. Now, this is all beautiful in theory, but we are, as we have been throughout, in the business of saying what was measured, what was actually observed. And the flux quantization was measured. In 1961, 2 independent experiments on opposite sides of the Atlantic confirmed it within months of each other. At Stanford University, Bascom Deaver and William Fairbank performed one of the experiments. In Germany, Robert Doll and Martin Neubauer performed the other. Both groups used similar ideas: thread a magnetic flux through a tiny superconducting cylinder, or hollow tube, and measure the flux that the cylinder locks in. Then change the applied field slightly and measure what the cylinder locks in now. If the flux is quantized, you will see it jump in discrete steps from one multiple of Fe0 to the next, rather than changing continuously. That is exactly what both groups found: jumps, discrete steps. The flux quantization was real, but the experiments returned something else as well. something that struck the physicists involved as an almost unambiguous message from the quantum world. The unit of flux they measured, the size of each step, was h divided by 2e, not h divided by e, not h divided by some mystery number, h divided by 2e, that factor of 2, that is the Cooper pair. If the charge carriers in a superconductor were ordinary single electrons, the denominator would be e. The flux quantum would be twice as large, but it was not. The denominator was 2e, twice the electron charge, meaning the carriers had charge 2e, meaning the carriers were pairs. In 1961, BCS theory was only 4 years old. The Cooper pair was a theoretical prediction that few physicists had yet fully internalized. And then Deaver and Fairbank at Stanford and Doll and Neubauer in Germany measured the size of the flux quantum and found it was half what single electrons would give. The factor of 2 was there, in the numbers, written into the magnetic field of a cold metal ring, waiting to be read. It was direct experimental confirmation that the charge carriers in a superconductor are bound pairs with charge 2e. It was BCS theory, proved not by spectroscopy or scattering, but by the arithmetic of magnetism. The metal was counting its magnetism in coins, whose denomination was determined by the pairing. And now we can close the loop that we opened at the very beginning of tonight's journey. The current that flows forever, the current that has not decayed in any experiment that has ever been run, whose decay time lower bound from measurement exceeds 100,000 years, whose theoretical estimated decay time is longer than the age of the universe. That current, in that ring, in that cold metal, why does it not stop? The answer now has a final piece. We said the current cannot decay because it is protected by the energy gap. Any event that would scatter a Cooper pair costs more energy than the cold can supply. We said the pairs are bound into a single condensate, so scattering one pair means scattering all of them, which is even more impossible. We said the current, once established, finds no path to zero that the cold can navigate. But there is something even more fundamental, something that the flux quantization now lets us say with full precision. The current in the ring is not just flowing, it is locked to a specific integer number of flux quanta threading the ring. Suppose the ring is carrying a current that produces, say, 3 flux quanta through its center, 3 times V0, 3 times that tiny unit of 2.07 x 10 to 15 Webers. The current and the flux are locked together. The current at that moment corresponds exactly to 3 quanta. Now ask, what would it mean for the current to decay? What would it mean for it to become slightly smaller? It would mean the flux became slightly smaller, but the flux cannot be slightly smaller. The flux can only be 3 quanta, or 2 quanta, or 1 quantum, or 0. Not 2.5, not 2 9/10, not 2 999 thousandths. To decrease the current by even the tiniest amount, the system would have to drop from 3 flux quanta to 2, a discrete jump, an abrupt change by 1 whole unit of F-Ulbrich. And that discrete jump is not a small event. It requires a macroscopic reorganization of the quantum state. The phase of the wave function around the entire ring must shift. The coherent state of millions upon millions of Cooper pairs must collectively change. This is not something a small thermal fluctuation can accomplish. At the temperatures where superconductivity exists, a few Kelvin, a few degrees above absolute zero, the thermal energy available is utterly insufficient to drive this transition. The current cannot gently bleed away because there is no gentle way to lose even a little of it. There is only an abrupt, energetically costly jump that the cold does not permit. So the current stays, not because nothing is trying to stop it, but because nothing that tries has enough energy to make the discrete leap. This is why we said earlier that the current's persistence is not a matter of friction being small, it is a matter of decay being forbidden. The word forbidden is the precise one. The laws of quantum mechanics applied to the superconducting state forbid the current from drifting. It can only jump, and it cannot afford the jump, so it stays. And now, the other question. The one that has been sitting quietly at the edge of the explanation, patient and important. Is this perpetual motion? The phrase perpetual motion carries a specific and precise meaning in physics. A perpetual motion machine of the first kind is one that produces work indefinitely with no energy input, that creates energy from nothing, in violation of the conservation of energy. A perpetual motion machine of the second kind extracts heat from a reservoir and turns it entirely into work, in violation of the second law of thermodynamics. The circling current in a superconducting ring is neither. It does not create energy. The energy for the current was put in once, at the beginning, when the current was first established, perhaps by slowly cooling the ring in a magnetic field and then removing the field, inducing the current by electromagnetic induction. That energy is stored, not created. It does not do work. The current circles in a closed loop. It has no load, no external resistance, no motor attached to it, no way to extract what it carries. It is not powering anything. The energy sits, stored in the magnetic field threading the ring, and nothing draws it out. It does not create anything from nothing. It loses nothing, but only because there is no mechanism by which it can lose anything without crossing an energy barrier the cold cannot surmount. The current is in a stable quantum state, as stable as an electron in the lowest orbital of a hydrogen atom. The electron circles the nucleus indefinitely. You do not call that perpetual motion in the forbidden sense, because the electron in the ground state simply has nowhere to go, no lower state to fall into. In precisely the same way, the supercurrent in a ring at zero flux quantum jump has nowhere to go. It is in its ground state, or a state locked by topology into a metastable form so robust that no perturbation available at that temperature can dislodge it. Perpetual motion of the forbidden kind violates conservation of energy. The supercurrent violates nothing. It persists not by breaking the rules, but by living so deeply inside the rules, the quantum mechanical rules of a coherent macroscopic state, that the usual mechanisms of dissipation cannot reach it. The current that flows forever in a ring of cold metal is the universe's way of showing you that some rules are so deep, so precisely binding, that they act like eternity. Not because anything magical is happening, but because the ordinary mechanisms of loss have been made by the cold and by the quantum completely impossible. And the magnet floats above the cold metal, held up by this same truth. It does not float because of a trick. It floats because the superconductor has expelled the magnetic field from its interior, actively and necessarily, as a consequence of the same deep quantum coherence that makes the current eternal. The Meissner effect is not a separate phenomenon from the persistent current. They are two faces of the same state. The expelled field is what you see from outside when the coherent quantum state inside is doing what quantum coherence demands. Meissner and Oxenfeld found this in 1933, before BCS theory, before Cooper pairs, before anyone had the language to explain it. They saw the field disappear from the interior of a lead sample as it was cooled through TC. They measured it, they reported it, and they understood, even without the full theory, that they had found something that distinguished a superconductor from every material anyone had ever studied. Something that was not just zero resistance, something new. The London brothers, Fritz and Heinz, 2 years later, wrote the equations that describe this behavior quantitatively. The London penetration depth, that thin surface skin, tens to hundreds of nanometers, where the field still lives before it is cancelled to nothing, comes directly from their equations. And their equations, it turned out decades later when BCS theory arrived, could be derived from the deeper quantum mechanical picture. The London equations are not wrong. They are the phenomenological surface of a deeper truth. And then Deaver and Fairbank, Doll and Neubauer in 1961 measured the flux quantum and found the factor of 2 and confirmed the pairs. The whole story hangs together. It is not a collection of disconnected facts. It is one story told at several levels of depth, from the surface, the floating magnet, the expelled field, down to the skin, the London penetration depth, the thin rind where the field decays, and then through the surface into the mechanism, the Cooper pairs, the macroscopic wave function, the energy gap, and then into the topology, the flux, quantization, the locked coins, the forbidden discrete jump. Every layer confirms the others. Every measurement points to the same picture. And somewhere, in a laboratory that might be running tonight, a ring of niobium or some other cold metal sits in a cryostat, cooled to a few Kelvin, with a current circling inside it that has been circling since someone first set it in motion perhaps years ago. No one is feeding it. Nothing is maintaining it. The apparatus around it hums and keeps the cold, and inside, in the dark, in a silence so cold that thermal vibrations are nearly stilled, the current goes around and around and around. The magnetic field threads the center of the ring, locked to an integer, multiple of 2/1000ths of a trillionth of a Weber. Outside the cryostat, the world goes about its business. People wake up and make tea. The sun rises and sets. Seasons pass. The current, inside, does not notice. It has been circling for longer than any of this night feels to you. It will still be circling after you wake in the morning. This is not a metaphor. This is a measured fact. The bounds placed on the decay time of such currents by experiment put the lower limit at 100,000 years. The theoretical arguments following from the physics we have been exploring together suggest the true lifetime would run to times longer than the present age of the universe, roughly 14 billion years, and then some large power of 10 beyond that. The current is, for any purpose you or I will ever have, forever. And here is the thing about forever. When it arises inside physics, it does not arise because someone decided to make something last. It does not arise from perfect engineering, from perfectly smooth metal, from some exceptional care. It arises because the laws of quantum mechanics, applied to the macroscopic condensate of paired electrons in cold metal, produce a situation in which decay is topologically forbidden. The current cannot bleed away gradually. It can only jump discretely by a whole quantum of flux. And the jump costs more than the cold can pay. Forever is the answer nature gives when you ask it to find a gradual path. And there isn't one. Take a moment to rest with that. The floating magnet above the cooled superconductor, that is the Meissner effect, the expelled field, the visible proof. The thin skin at the surface, those tens to hundreds of nanometers, where the field still exists before decaying to zero. That is the London penetration depth described by Fritz and Heinz London in 1935. The quantized coins of magnetic flux locked to integer multiples of H2E, that is flux quantization, measured in 1961 by Bascom Deaver and William Fairbank at Stanford, and independently by Robert Doll and Martin Neubauer in Germany, the factor of 2e in the denominator, a direct reading of the Cooper pair written into the magnetism of the metal, and the current that cannot decay, not gradually, not slowly, not at all, because the only path to decay is a discrete jump that the cold energy forbids. That is the persistent current, the thread that runs through the whole story, the thing we began with in the first quiet moments of tonight. The mechanism is complete. The pieces are all here now. But there is more to the story, because the superconducting state has a boundary, a surface beyond which it cannot reach. And that boundary is itself a rich and structured thing. And there are kinds of superconductors that admit a more nuanced relationship with the magnetic field than the complete expulsion of the Meissner effect. And there are instruments built from the principles we have been exploring that can detect magnetic fields so faint they are almost unimaginable. And there is a family of materials discovered in the 1980s that superconduct at temperatures once thought impossible, cooled not by liquid helium but by ordinary liquid nitrogen. And the mechanism behind those materials is, to this day, one of the genuinely unsolved problems in physics. All of that waits just ahead in the next passage of tonight's journey. But for now, let the picture settle. The magnet floats, the field is expelled. The penetration depth is 30 nanometers or 100 or 200, depending on the metal. A layer you could not see with any ordinary microscope, a ghost of field at the surface. The flux through the ring is an integer. The current is forever. The Cooper pair wrote its own name into the denominator of the flux quantum, and Deaver and Fairbank and Doll and Neubauer read it out of the measured number in 1961, and the book has been open ever since for anyone willing to sit quietly with the cold and listen. Wherever you are tonight, whatever time it is in your corner of the world, whatever lamp is still on, whatever quiet is around you, the physics we have been walking through is the physics of this same world, this same universe, the one you are lying in right now. The quantum rules that lock the current in the ring are the same rules that govern every electron in every atom of every material around you. Most of the time, those rules are hidden, averaged away by warmth and disorder. In the cold of a superconducting ring, those rules become visible. The quantum world, usually so shy, steps forward and makes itself known. It says the flux is an integer. The current does not decay. The field is expelled. These are not approximations. These are exact. No rush to follow all of it. The current is patient. It will keep circling while you drift. And the story continues in just a moment with the boundary, the edge of the superconducting state, and what waits just beyond it, and what happens when the cold metal meets a world that pushes back. So let us talk about the boundary. Everything we have walked through so far, the forever current, the Cooper pairs, the shared wave function, the flux counted in indivisible coins, all of it exists inside a kind of sanctuary, a protected space. And like any sanctuary, it has walls. Cross the wall, and the magic dissolves. The quantum order that took such intricate care to build collapses back into ordinary, resistive, warm metal, all in an instant, the way a soap bubble does not thin and fade, but pops, simply, completely, with no intermediate stage. The sanctuary has three walls. The first one you already know, temperature. The critical temperature, Tc, the threshold below which the superconducting state exists and above which it does not. For Mercury, it sits at about 415 Kelvin, barely 4 degrees above absolute zero, a cold so extreme that almost nothing in the natural universe achieves it spontaneously. For lead, it is 7.2 Kelvin. For niobium, the champion among the pure elemental metals, 9.3 Kelvin. These are the temperatures Ons and everyone who followed him had to reach and hold and defend, measuring in fractions of a degree, keeping the liquid helium topped up, watching the instruments with care. A thermometer that drifts by a single degree in the wrong direction is a thermometer that has just destroyed the state you spent hours building. The intuition is not hard to feel. The Cooper pairs that carry the supercurrent are bound together by the lattice dimple, the tiny whisper of attraction mediated by phonons, and that binding is fragile. The energy of that bond is measured in millielectron volts, a unit so small that room temperature thermal jostling absolutely dwarfs it. At 300 Kelvin, the ordinary temperature of a comfortable room, the thermal energy available to every electron is something like 50 times the pairing energy. the pairs would be shredded instantly the way a cobweb is shredded by a gust of wind. So warmth is the enemy, and the cold is the refuge, because only in the cold does the thermal energy drop below the pairing energy, below the gap, below the threshold, where the lattice whisper can actually bind two electrons together and keep them together long enough to matter. Cross the temperature wall, and the pairs break. The shared wave function dissolves. The current, which was circulating without any dissipation, now encounters the full resistance of a normal metal. Every electron scattered by every imperfection and vibration in the lattice, and it vanishes in a fraction of a second as though it were never there. The second wall is stranger and requires a moment to sit with. Magnetic field. There is a critical magnetic field by something called Hc, above which the superconducting state cannot survive. Apply a strong enough external field to your superconductor, and it loses its superconductivity, even if the temperature is still comfortably below Tc. This surprised early researchers who had perhaps thought of the two phenomena, the zero resistance and the field expulsion, as separate properties. They are not separate. They are different faces of the same quantum state. And when the field is strong enough to threaten the state collapses entirely. Think of it this way: the Meissner effect, which we spent time with earlier, the expulsion of the magnetic field from the interior of the metal, requires effort. Not effort in the human sense, but in the thermodynamic sense. The superconducting state, to maintain its field-free interior, must generate surface currents that push back against the external field. Those currents cost something in the accounting of the condensate's energy. When the external field is small, the superconducting state is still the lower energy option and the system stays superconducting. But as the field increases, the energy cost of expelling it grows. Eventually, what at Hc, then the normal resistive state becomes thermodynamically cheaper. The superconductor gives up. It lets the field in, and in doing so it reverts to ordinary metal. The third wall is current itself. The same electrons that carry the persistent current also generate their own magnetic field. Every moving charge does. If you push too much current through the superconductor, or if the current circulating in the ring grows too large, the field generated by that current can eventually approach the critical field, and the superconductor, unable to hold against the combined assault of its own current's magnetic field, collapses. This is the critical current density, Jc. It sets a hard ceiling on how much current a superconducting wire or ring can carry before the very act of carrying it destroys the state that permits it. 3 walls, 3 limits: temperature, field, current. They define not 3 separate boundaries, but a single surface in a 3-dimensional space, and the superconducting state lives only inside that surface. The material is superconducting wherever T is less than Tc, wherever H is less than Hc, wherever J is less than Jc. Wander outside in any direction, heat it, or magnetize it, or push too much current, and you step out of the sanctuary and into the ordinary world. This is a useful thing to know, and also in its own way a beautiful thing. The superconducting state is not infinitely robust. It is a delicate phase held together by the faintest of quantum whispers, and it requires exactly the right conditions to persist. The wonder is not that there are limits, but that the state exists at all. That there is any region of temperature and field and current within which the quantum rules can organize themselves so precisely that a current set flowing in a ring will circle and never stop. Now, inside that sanctuary there is still more texture to find, and to find it we need to make a distinction that turns out to matter enormously. Not all superconductors are the same. The ones we have mostly been talking about, mercury, lead, tin, the pure elemental metals, belong to a category called Type Y superconductors. They are the clean, simple case. Below Tc and below hRc, they expel the magnetic field completely, maintaining a perfectly field-free interior right up until the critical field is reached. Then, all at once, the field rushes in and superconductivity collapses. There is no middle ground. The Meissner effect is total, and when it fails completely. But there is a second category, and it behaves quite differently. Type II superconductors. The alloys and compounds, things like niobium titanium and niobium tin, have not one critical field, but two. Below the first, the lower critical field, they behave just like type Y. Total field expulsion, complete Meissner effect, a clean and perfect interior. But between the lower and the upper critical field, something strange happens. Instead of collapsing entirely, the superconductor finds a compromise. It allows the magnetic field to penetrate, but not in a continuous, uniform way. The field squeezes through in discrete, thin tubes, each tube carrying exactly one flux quantum, exactly one F0s. Each of these tubes is a flux vortex, a tiny filament of magnetic field threading the superconducting material, surrounded by a tiny whirlpool of circulating current that keeps the field contained within the tube and shields the rest of the material from it. The material between the vortices remains fully superconducting. Only the cores of the vortices themselves are driven normal. So in this mixed state, the superconductor is neither fully superconducting everywhere nor fully normal. It is a kind of lattice of tiny normal cores, each carrying one quantum of flux, set in a sea of still superconducting material. And those vortices, given the chance, arrange themselves into a pattern. The prediction was made by Alexei Abrikosov, and it is one of the more beautiful pieces of theoretical physics of the 20th century. Abrikosov showed that the flux vortices in a type II superconductor would naturally arrange themselves into a regular triangular lattice, the closest possible packing of the tubes, minimizing their mutual energy. This pattern, called the Abrikosov lattice, or sometimes the Abrikosov vortex lattice, was later confirmed experimentally. If you could look at a cross-section of a type II superconductor in its mixed state, you would see this exquisitely regular triangular grid of tiny flux tubes, each separated from its neighbors by the same distance, tiling the material like a honeycomb printed in magnetic field and supercurrent. Abrikosov received the Nobel Prize in Physics in 2003 for this work, along with Vitaly Ginzburg, work that had been done in the 1950s and sat, sometimes unacknowledged in the West, for decades before the full weight of it was recognized. The practical importance of type II behavior is this. Because the mixed state allows partial penetration of field while remaining substantially superconducting, type II materials can maintain their superconductivity up to much higher fields than type Y materials can. For a pure metal like lead, the critical field is modest, a few hundredths of a Tesla, not enough for the most demanding applications. For niobium titanium, a type II alloy, the upper critical field is many Tesla. For niobium tin, it is higher still. This is what makes type II alloys the materials of choice for the powerful superconducting magnets that live in research laboratories, and as we will come to in a moment, in a piece of medical equipment that many people have encountered firsthand. But first, a phenomenon so delicate and so strange that it deserves its own quiet moment. In 1962, a graduate student at Cambridge named Brian Josephson was thinking about what would happen if you took two pieces of superconductor and separated them by a very thin layer of insulator, thin enough that quantum mechanics matters, thin enough that particles can do the thing quantum mechanics uniquely permits, tunnel through a barrier they classically have no right to cross. An ordinary electron, you might expect, would be stopped by an insulating barrier. But Josephson asked what would happen to a Cooper pair, to the entire condensate, when it encountered such a barrier. And what he found, theoretically, was that the macroscopic wave function of one superconductor could couple to the macroscopic wave function of the other through the barrier. The phase of the wave function, a quantum quantity that had previously seemed like a mathematical bookkeeping device, turned out to be physically real in this context, physically measurable and physically consequential. Josephson predicted that a current of Cooper pairs could flow across the insulating gap with no applied voltage whatsoever, a supercurrent through an insulator. He also predicted that if a voltage were applied across the junction, the current would oscillate at a precise frequency directly proportional to that voltage, a relationship so exact and so fundamental, depending only on twice the electron charge and Planck's constant, that it became one of the most precise measurements in physics. He made these predictions in 1962. He received the Nobel Prize in Physics in 1973, sharing it with Leo Esaki and Ivar Giaever. He was, at the time of his prediction, a doctoral student. The Josephson junction, as the thin barrier device came to be called, is the building block of the SQUID. The SQUID stands for Superconducting Quantum Interference Device, and it is, without serious competition, the most sensitive magnetometer that exists. It works by exploiting the interference of two quantum paths, two Josephson junctions connected in a loop, and reading out the tiny shifts in phase caused by any magnetic field threading the loop. The sensitivity it achieves is not a little better than other instruments. It is not twice as good or 10 times as good. A SQUID can detect magnetic fields approximately 100 billion times weaker than the Earth's own magnetic field. Pause on that for a moment if you can. The Earth's magnetic field, the one that pulls compasses north, that guides migrating birds, that you can feel the edges of if you hold a compass very still. A SQUID can detect fields 100 billion times smaller than that. It can measure the tiny magnetic fields produced by electrical currents flowing in the human heart. It can measure the even tinier fields generated by currents in the human brain. It makes measurements that no classical instrument, no matter how refined, could approach. And it does so by being, at its core, a quantum device, a device that treats the superconducting wave function not as a curiosity but as a measuring instrument. Whenever you are ready to drift a little further, we can take the persistent current from the laboratory ring and let it do a specific job. In some of the most powerful superconducting magnets in existence, in particle accelerators and in research laboratories and in hospital imaging rooms, the current is not supplied by a continuously connected power source. Instead, once the magnet has been energized to its operating level, the external power supply is gradually disconnected. The two ends of the superconducting coil are joined together by a short length of superconducting wire, a persistent switch, and the current is allowed to circulate on its own, exactly as in the ring we have been imagining all evening. The magnet is now running in what is called persistent mode. In persistent mode, the current has nowhere to go. It circles through the coil and back through the persistent switch in a closed loop, and the only thing that could stop it is a rise in temperature above Tc, or a field exceeding Hc, or a current exceeding JRC, none of which in a properly maintained system are permitted to happen. The power supply, which has done its work, can be shut off. The magnetic field inside the magnet, produced entirely by this circulating persistent current, remains. Not quite perfectly in practice. In practice, tiny imperfections in the joints between sections of superconducting wire, junctions that are close to superconducting but are not perfect, allow a vanishingly small amount of drift. The field in a well-made research or medical superconducting magnet in persistent mode decays at a rate typically specified as a handful of parts per million per hour, perhaps 1 part per million per hour, or 2 or 5. The number varies by instrument and by the care taken in its construction, but notice what that number means. 1 part per million per hour is, on a human timescale, essentially nothing. The field is stable enough to perform the most demanding magnetic resonance measurements, stable enough that the drift is a footnote rather than a problem, stable enough that the magnet can be left running, untouched, self-sustaining, carrying its circulating current for months or for years. The magnet in an MRI scanner, in the machine that clinicians use to image the human body in extraordinary anatomical detail, is at its heart a superconducting ring in persistent mode. There is liquid helium, cryogenically sealed, keeping niobium titanium wire below its critical temperature. There is a circulating current, set running once when the machine was installed and energized, and circulating still, right now, in every hospital where such a machine sits. In the quiet hospital corridor behind the closed door of the imaging room, a current is flowing and not stopping. It will not stop tomorrow. It will not stop next year. It is the same phenomenon made practical and useful that Onnes first glimpsed when Mercury's resistance read, on his instrument, as practically zero. Take a breath. Let that settle. There is one more family of connections worth making, if you are still with us. Some cousins to the superconductor, and an open question that the world's best physicists have not yet answered. The cousin first. In 1937, three researchers, Piotr Kapitsa in Moscow, and independently John Allen and Don Misener in Cambridge, discovered something strange about liquid helium. When liquid helium is cooled below about 2.17 Kelvin, a temperature called the lambda point because of the shape of the specific heat curve, near that threshold, the liquid undergoes a phase transition into a new state. It becomes a superfluid. A superfluid flows without friction, not with very little friction or without any. If you set liquid helium spinning in a container and then cool it below the lambda point, it will spin without any viscous damping, without any tendency to slow down and come to rest. Pour superfluid helium into a container and it will flow up the walls and over the edge and drip out the bottom, defying gravity if given the slightest encouragement. A thin, invisible film of frictionless liquid making its way over any surface it can reach. It passes through channels so narrow that any normal liquid would be completely blocked. The relationship between superfluidity and superconductivity is deep, and it is not merely analogy. Both are macroscopic quantum states. Both arise because a vast number of particles condense into a single coherent quantum ground state. In the superconductor, the particles are Cooper pairs, charged bosonic objects responding to electromagnetic fields. In the superfluid, the particles are helium atoms, neutral, not charged, not coupled to magnetic fields the same way. The superfluid is, in a loose but illuminating sense, the neutral cousin of the superconductor, the same organizing principle, the same macroscopic wave function, the same protection against dissipation, but expressed in an uncharged fluid rather than in a charged metal. Neither friction nor resistance, the same deep quantum reason beneath both. And there is one more small thing, sitting quietly at the edge of the story, that feels worth mentioning. A rotating superconductor generates a magnetic field aligned with its rotation axis. This is the London moment, a name for Fritz and Heinz London, whose equations laid the theoretical groundwork for so much of what we have been discussing. The field is tiny, extraordinarily tiny, but it is there, and it is real, and it was used in an experiment called Gravity Probe B, a NASA mission that flew a relativity experiment in orbit, to read out the orientation of gyroscopes made from superconducting spheres. The London moment was the signal. The superconductor, in other words, turned itself into a precision measurement device by way of its own rotation. A rotating macroscopic quantum object broadcasting its orientation through a magnetic field. Something about that image, if you let it sit, a gyroscope spinning in space, its quantum state printed into the field around it, feels like a fitting emblem of everything superconductivity is, the quantum world, made large enough and cold enough and still enough to reach out and be measured. And now, the open question. The honest, unresolved, genuinely mysterious open question. In 1986, two researchers at IBM's Zurich Research Laboratory made a discovery that shook condensed matter physics in a way nothing had since the original discovery in 1911. Georg Bednorz and K. Alex Miller were studying ceramics, layered copper oxide materials called cuprates, and they found that one of these ceramics, a lanthanum barium copper oxide compound, became superconducting at approximately 35 Kelvin. 35 Kelvin does not sound impressive on first hearing, but put it in context. BCS theory, which had been so successful at explaining conventional superconductivity, had generally led physicists to expect that the critical temperature of any superconductor would top out well below 30 Kelvin. The theory's framework seemed to set something like a ceiling, a practical upper limit on TC. Bednorz and Miller had apparently crashed through the ceiling. 35 Kelvin was startling. What happened next was more startling still. Within months, other research groups around the world were racing to find other cuprate superconductors, pushing the critical temperature higher. In 1987, the very next year, a compound called yttrium barium copper oxide was found to superconduct above 90 Kelvin. It is sometimes called the 1-2-3 compound from the ratios of its components. 90 Kelvin is above 77 Kelvin, and 77 Kelvin is the boiling point of liquid nitrogen. This matters because liquid nitrogen is cheap, it is abundant, it is, by cryogenic standards, almost ordinary. It is used in food preparation, in industrial processes, in medical procedures, in a dozen applications far beyond physics research. Liquid helium, by contrast, requires careful handling, specialized equipment, and significant cost. The original superconductors required helium temperatures. The new cuprates could be cooled by nitrogen. Bednorz and Müller received the Nobel Prize in Physics in 1987, awarded with remarkable speed. The discovery was less than 2 years old when the prize was announced, one of the fastest recognitions in the history of the award. But the cuprate superconductors brought with them a problem that has never been solved. The BCS theory, with its Cooper pairs coupled through phonons, works beautifully for conventional superconductors. For the cuprates, the high-temperature superconductors, it does not work. The pairing mechanism, whatever it is not the simple phonon-mediated interaction that BCS describes. The Cooper pairs in cuprates appear to still be pairs of electrons. The factor of 2e in the flux quantum is observed in high-temperature superconductors too, confirming pairing. But how those pairs form and what binds them remains, as of the best current understanding, genuinely, openly, professionally uncertain. This is not a small gap in knowledge that a few more experiments will close. The mechanism of high-temperature superconductivity in the cuprates is one of the major open problems in condensed matter physics, widely acknowledged as such, and many of the best theoretical physicists of the last 4 decades have worked on it without arriving at a consensus. The phenomenon exists. It has been measured exhaustively. Its characteristics are known in great detail. And yet the deep theoretical question, what is binding these electrons, what is the cuprate equivalent of the phonon dimple, has not been answered to the satisfaction of the field. There is something quietly wonderful about that if you let it land softly. We have been walking through a subject tonight that is, in the case of conventional superconductors, settled science, understood, verified, reproduced, built upon. The BCS picture and the flux quantization and the London equations and the Meissner effect are not hypotheses, they are confirmed, precise, beautiful mechanisms. And yet at the edge of the same subject, there is a door that remains closed. The cuprates superconduct, no one doubts that. But the full reason why the complete account is still being written. The universe keeps a few things for itself. And so, We have walked a long way tonight, you and I. We began in a cold laboratory in Leiden sometime before dawn, sometime before the world knew that the rules of the very small could organize themselves at the scale of the very large. We watched a thread of mercury go strange, the needle of an instrument settling towards zero and not stopping, the resistance not merely shrinking but disappearing, the experimenters suspecting a short circuit and then carefully ruling it out and finding themselves with something that had no name yet. Heike Kamerling Onnes and his notebook and the line he wrote in Dutch, Quick Nagenoig Nul. Mercury practically zero. We traced what that zero means, and we found that it means something far deeper than a very good conductor. It means a metal that has entered a new state of matter, a state in which millions of electrons have given up their individual identities and merged into a single quantum object, a macroscopic wave function coherent across the full length of the ring, coherent across every atom of the metal, describable by one equation, one phase, one amplitude. It is not that the electrons have stopped scattering, it is that the thing doing the traveling is no longer an individual electron but a collective state, and to scatter one electron in that state would require changing the whole state at once, and the cold, quiet world cannot pay for that. We found the Cooper pairs, not because John Bardeen and Leon Cooper and John Robert Schrieffer invented them, but because the mathematics required them, and because the lattice, flexing slightly under the passage of one electron, creates a transient invitation that a second electron accepts. Partners that never touch, bound by a whisper, mediated by the vibrating lattice, by phonons. And because they pair into objects with integer spin, they are no longer fermions constrained by the exclusion principle. They are, collectively, bosons, free to pile into the same quantum state, free to share one wave function, free to become the forever current. We found the energy gap and the locked door, the milli-electron volt minimum that any disturbance must pay to break a pair and push an electron into the normal world. In the cold, nothing has that energy. In the cold, the lock holds. We found the Meissner effect, or the visible proof of the invisible rule, the moment where the abstract becomes something you can see with your eyes, a small magnet hanging in the air above a cup of cold metal, held up not by wires or tricks, but by a fundamental property of the quantum state. The field is not merely absent from the interior of the superconductor, it is pushed out, expelled, rejected. The surface currents flow exactly as needed to cancel the field inside. The copper oxide ceramics that Meissner and Oxenfeld cooled in 1933 were telling them something that took another quarter century to fully understand. We found the flux quantum, the indivisible coin in which the ring counts its own magnetism. The number h divided by 2e, approximately 2.07 times 10 to the negative 15 Webers, a number so small it has no intuitive scale. And yet a number that is exact, that is fixed, that admits no fractions. The flux through the ring must be 0, or 1 flux quantum, or 2 or 3. Nothing in between is permitted by the mathematics of the wave function, and to change from one integer to the next is a step that requires the entire condensate to rearrange at once, a coordinated quantum leap that the ordinary cold cannot coerce. So the current is locked. And Bascom Deaver and William Fairbank at Stanford and Robert Doll and Martin Neubauer in Germany measured this in 1961 and found the factor of 2e in the denominator. And with that factor, they confirmed that the charge carriers are pairs, that Cooper was right, that BCS was right. We found the boundary surface, temperature, field, current, 3 walls of the sanctuary. And we found that there are 2 kinds of superconductors, and that the type 2 ones, with their Abrikosov lattice of quantized flux tubes threading the material like an exquisitely regular honeycomb, can hold their quantum state against far stronger fields. We found Brian Josephson's tunneling prediction and the squid and a sensitivity to magnetic fields so fine it reaches things as delicate as the electrical murmur of the human heart. We found the persistent current doing its steady job in the magnets that live in hospital imaging rooms, circulating in a closed loop with no power supply, drifting by perhaps 1 part per million per hour, stable enough for decades, sustained by nothing but the cold and the quantum rules. We found superfluid helium below the lambda point, frictionless, climbing walls defying intuition, as the neutral cousin of what the superconductor is, both of them expressions of the same organizing principle, the same condensation of many into one. And we found the open question, the honest, not yet answered place at the edge of the map, where the cup-rate superconductors sit with their high critical temperatures and their still uncertain mechanism, where the world's best physicists have spent decades and not yet agreed, where the phenomenon is real and the explanation is incomplete and the universe has not yet given up the last secret. This is how physics goes in the end. Some doors open cleanly and you walk through and find another room you understand. Some doors are still locked and you can see the light under them, but you cannot yet see what is in the room. The permanently flowing current in the ring is a door we walked through fully tonight. The cuprate mechanism is a door with light under it, and some of the best minds alive are still working on the lock. Both are worth knowing, both are part of the same subject, and both, the understood and the mysterious, share one quality that I find, in the late quiet of a night like this, genuinely comforting. They are real. They happen. The current flows, the magnet floats, the flux is quantized, the superfluid climbs the wall. These are not stories or hypotheses or useful fictions. They are measured, verified, reproduced in laboratories on every continent, confirmed to extraordinary precision across decades of careful work. The universe chose to make itself this way, and we, by being patient and cold and precise, got to find out. You are, right now, lying in a world governed by these same rules. The electrons in every atom around you, in the wall beside you, in the metal of whatever lamp is still on, in the materials of everything, are subject to the Pauli exclusion principle. Our fermions, obeying exactly the laws that BCS described, are potentially capable of pairing if only the temperature dropped far enough. At room temperature, the thermal noise is too loud, the vibrations too strong, the energy too high for the whisper of the lattice to bind anything. Everything is warm and ordinary and resistive, but the rules are still there. Underneath the warmth, underneath the disorder, the quantum rules are written into every electron, into every atom, into the material of this room and this night. The superconductor is not a place where special rules apply. It is a place where the ordinary rules, usually hidden, become visible, where the quantum world stops being shy and shows itself plainly, the way a star becomes visible only when the sky around it darkens. You do not need to do anything with this. You do not need to hold the equations in mind. It is enough, I think, to have spent some part of tonight in the company of the idea that somewhere in a cold laboratory, a current is circling in a ring of metal, and it is not slowing down, and it will not slow down, and this is not magic or metaphor, but physics, exact and verified and strange and beautiful all at once. I asked at the very beginning of tonight where you are listening from. Whatever corner of the world you are in, whatever time it is, whatever weather is outside, whether you still have a lamp on or whether it has long since gone dark, you carried that question with you through Leiden in 1908 and through Mercury going still and through Cooper pairs forming in the cold and through the magnetic field being expelled and the flux counted in coins and the current circling without end. The current is still circling. It will be circling when you wake. The physics will be here, unchanged, patient as the cold itself. If you enjoyed this slow drift through something genuinely strange, a gentle like or a subscribe to the Curious Voyager means more than you might expect. This is a small, quiet channel, and small creators like me rely on your support to keep these journeys going. And I would love to know, where in the world are you listening from tonight? And what time is it in your corner of the dark? Leave it in the comments if you feel like it. It is always a pleasure to know. Sleep well, fellow Voyager. The next journey keeps until you wake.